Hello everyone, my name is Jay Joshi, and this is my partner, Daniel Webster.
Hi everyone.
And today we will be presenting to you our battleship project in our databasing class.
To start things off, we'll introduce the general market, purpose, and audience of our system. The general market of our system is mainly adults that want to play the game with their family, or that want to play the game with their children, or have the game for their children to play.
The purpose of our battleship system is to generate a database, only a database, not the actual game, that simulates the experience of the board game Battleship.
Now, the audience that our system targets is children around the ages of 5 and up. Now, the reason we choose 5 and up is because we're going based off the assumption that anyone under the age of 5 would not be able to follow the flow of the gameplay.
Now, moving on to our functional requirements, our first functional requirement is that ships need to be placed on the grid. This is essential for the functionality of the game. You cannot start to play the game without having ships placed on your grid.
The second functional requirement that we chose to implement was that each player will take turns trying to sink the other player's ships. We made this a functional requirement because it's necessary for the game. It is basically the main purpose of the game.
Now, the third and fourth requirements kind of go hand in hand here. The third one is whether a ship was hit or not needs to be declared upon declaring the target coordinate. And the fourth requirement is that ships that are sunken need to be declared so. So a ship is sunken if all of its target coordinates are marked with hit markers. And we need this to be declared to the players so that they know how many coordinates they have hits, how many coordinates they have misses, and how many ships they've sunk. This adds the aspect of strategy to our game.
The last functional requirement we chose was declaring the winner at the end of the game. Well, we could have went about two ways of doing this. We could declare who won the game or who lost the game, or do both. But we decided to just include the winner of the game. This is more of a reward-based aspect of the game rather than declaring a punishment for losing. So next we're going to go right on into the non-functional requirements. The first non-functional requirement that we chose was that no ships can overlap other ships. What we mean by this is that you can't have two ships on top of each other, because when your enemy shoots upon your ships, they can essentially hit two ships with one shot, and this shouldn't be allowed in the game.
Our next non-functional requirement is that all ships on either player's board will only be allowed to be placed within the 10 by 10 boundary of the grid and cannot transcend that boundary. This is an essential rule. If you transcend the boundary, then ships become untargetable, or the range for the ships can become so immense that the game could take too long to finish.
The third non-functional requirement is that each player can only have 5 ships on their respective board. This is a scalability restriction that we chose because for our sake, we decided that 5 was a suitable number, and it is the number that Hasbro uses for their ships. In the future, you can decrease the amount of ships or increase the amount of ships depending on the kind of game that you would like to change, or how you would like to change the game in the future.
Now, our fourth non-functional requirement is that neither player will be allowed to view the opposing player's grid, or screen in this case. This is very essential because if you can see the opposing player's grid and where their ships are located, you can win automatically. It defeats the purpose of the game, of the competitive strategy, of everything. By restricting a player's view of the grid to only their own, that's how the game is played.
The fifth non-functional requirement that we chose was based upon response time. We decided that any input that the game receives, it should respond within 2 seconds. We decided on this because when you play a game, you don't want to wait an extended loading time or buffer time for the game to react.
Now, moving on from our requirements, we have our entities and our properties of our database. Our 3 main entities for our database are players, which represent player 1 and player 2, ships, which represent the 5 different ships a player can have, as well as their names and their lengths, and the boards, which represents player 1's grid and player 2's grid.
Between these entities, we decided to include properties that we thought were important to the functionality of these entities. Amongst these properties, we chose player names, ship sizes, coordinates, the hit and miss marker, whether a ship is sunken or not, and the location of the ships.
Once again, we felt that these properties were most important to understanding the relationship between the three entities of our database.
Alright, so moving right along, as you can see here, we have a entity relationship diagram. This visually represents the entities that we have and the relationships between them. Each entity has a many-to-many relationship with its corresponding entities. From the entity relationship diagram, we constructed a relational schema.
Now, this shows the relationship between the tables themselves in our database. Now, since there are two players, we don't want a player being able to view the information in the other player's database. So what we did is we created junction tables in between two main entities so that player 1 only has access to one junction table while player 2 has access to another junction table. So player 1 can only see his coordinates, his grid, his ships, and player 2 can only see his version or his own side.
Because we did this, it did cause duplicates of tables that could normally be created into one table, but we thought for the purpose of security that it was okay that we had these duplicates.
So while we're talking about tables, let's discuss the normalization of the tables in our database. Now, 8 out of 9 of the tables in our database all contain the coordinates attribute, and because of this, they violate the first normal form of atomicity. And this is because each coordinate contains a letter value for the horizontal axis and a number value for the vertical axis. And what this does is it combines these two into one coordinate, and while we do violate atomicity, we do allow for not having as many duplicates as having separate cells containing individual letters and individual numbers, and instead we have individual cells containing unique coordinates for each grid.
Alright, so let's talk about the keys of our tables. As you can see from the relational schema, our keys are marked by yellow exclamation marks. The primary keys in our main entity tables, table coordinates, table ships, and table players, are as follows: coordinates, ship name, and player name. These three primary keys act as foreign keys in other tables. The junction tables. The junction tables have primary composite keys that consist of the foreign keys that are related to the primary entity tables. We have many relationships and many junction tables, and this causes for many keys. This leads us on to our next point, indices.
The only indices that we chose to include into our database were the indices that were automatically made by the primary keys. We felt that since the database was small enough just to have maybe 100 rows at the most of data, that adding in an index would only minimally maximize or make our database faster. So in that sense, we thought that without indices, it wouldn't make that much of a difference.
Moving right along, now we'll talk about some non-trivial queries. We were requested to create 5 non-trivial queries. The first time we attempted to create the non-trivial queries, we weren't very successful. This is mainly because our tables were designed for simplicity for us. We ignored a lot of best practices and created very trivial queries for our benefit. The second time around, we fixed our tables, and those were the ones we showed to you earlier. Here's an example of one non-trivial query that we were able to come up with. As you can see from the picture, in the top left corner, this query is a trigger. It calls the procedure hit miss. This procedure is displayed on the bottom left corner. What this procedure does is it checks which player is targeting the coordinate. From here it calls another procedure. Depending on the player, it'll call P1 ship at coord or P2 ship at coord. What these procedures do, which are displayed on the right, is checks if the target coordinate corresponds to the location of a ship. The procedures are exactly the same, but check varying on which player is selecting the target. These procedures call an update that set the value of hit to either true, which is 1, or false, which is 0. This is just one example of our non-trivial query.
So this concludes our Battleship database project. Today we went through in detail our functional requirements, our non-functional requirements, the entities and their individual properties, the entity relationship diagram, the relational schema, how we normalize the tables, the keys that we set for our tables and the indices, and finally we showed you an example of one of our non-trivial queries. We hope that you enjoyed this presentation, and if for whatever reason you have questions or comments, please feel free to ask us. Thank you very much and have a great day.